Newton's second law in angular form. Torque revision. We talk about the torque, a force F, okay, relative to a point O, because the torque is R cross F, okay. This is the acting point, this is R, okay. R cross F means this torque is perpendicular to R. A torque is perpendicular to F. So in this case, when you use the right-hand rule, we go to R cross F. So the torque is along the positive direction. Okay. This is definition. And we rewrite it, and the cross product of the two vectors equal to RF sine phi, and the direction torque is V. And we combine F and sine phi, we get, because we call it RF perpendicular torque. What is it? Let's see that one. This is a phi, angle between F and R. This is a phi. F sine phi is this one. This one is the F's component perpendicular to R, okay? Also, we can combine R sine phi, because F R sine phi. What is R sine phi? R sine phi, we call it R perpendicular. What is this? You look at this one. This is F, this is R, this is phi. R sine phi is this one. This one is the component of R perpendicular to F. So finally, torque equal to RF perpendicular or FR perpendicular. Torque has a meaning only with respect to a specified origin. Here is the O. If F parallel to R, then phi is 0. Sine 0 is 0. That means torque is 0. Okay. The torque tends to rotate the body. Sample. In figure A, forces each of magnitude 2.0 Newton act on a particle. This is a particle. You have a three force, F1, F2, F3. Okay. The particle is in the XZ plane at point A, given by position R, this is R, okay, where R is 3.0 meter and theta is 30 degrees. Force F1 is parallel to the x-axis. Force F2 is parallel to the z-axis. And force F3 is parallel to the y-axis, or towards the negative direction. What is the torque about the orange O due to each forces? We look at this one. We find the torque 1. By definition, torque 1 is R cross F1. We look at this one. This is F1 along X minus C. So we look at XOZ. We move the R up. So this is R, this is F. So we use the right-hand formula. We wrote this one. We find the torque one is inward the space, this place. So it's XZ is minus Y direction. Okay, and the magnitude is F1 sine phi. The angle you look at is 150. The direction is inward. This one is minus Z, minus Y direction. So this is X, Y, Z. The tall one is minus Y direction. Let's look at torque 2. F2 is here. So they are in XOZ surface. We moved R out. You see this angle, this is 30. So this is 90, so 120. Okay? And you use the right-hand rule, you move this one here, you find the direction is outward the surface. Okay? That one is the positive Y direction, X, Y, Z. Okay? The number is R F2 sine phi. That's phi 120. Okay? And the last one is F3, this one. So torque, this is R. We move this one, we find this F3. We look from X or Z direction is inward. Okay, this R. So use the right hand rule. R cross F is this one. It is also in the X or Z plane. Okay, and this is perpendicular to R. So this is this one. R3. The angle is 90 degrees. Okay. This is 3. Okay. And in mathematics, the cross product of two vectors can be expressed in matrix. IJK. This is XYZ. This is FX, XY, FZ. For example, in this case, okay, Rx is R cosine theta. Ry is 0. Iz is I sine theta. Look at F. F1 is minus F. F1 is Y 0, F1 0. So this one, if you extend this matrix, you get a minus Fij is equal to minus 3.0 Newton J. Exactly this equal to this one. Okay. Angular momentum. We define for a single angular momentum particle is equal to R cross P, where R is its location, okay, the position, acting point R. The P is linear momentum, mv, okay, and the m can take out m at the side. This is the definition, okay. Now let's look at this angular momentum carefully, okay. We know this is always right hand rule. We extend our right hand along the 4 fingers along the Y, and we rotate towards the P. That your extended thumb is the direction of air. Okay. Now we look at this one. The air perpendicular to R, perpendicular to V. So the air must be this one. Okay. The angular momentum in this case, because R cross P, so it's up, it's this right direction. Okay. We write this one. This is a unit angular momentum along the Z direction in our case. Okay. The magnitude is mv r sine phi. The phi is the angle between the velocity p, angular momentum equal to r cross p. This is r, this is a p, okay? This is angle phi between them. We can combine the sine phi with different things, okay? They all have r, so we have to specify what kind of orange it is. Okay. Then we rewrite the magnitude, no direction. It's mrv sine phi. We can combine mv with sine phi. You can see mv sine phi is this one, p perpendicular. Perpendicular to what? Perpendicular to r. Okay. Also, we can write this one. Okay. We combine r sine phi. Okay. What is r sine phi? Look, this one. This is r. This is the phi. I sine phi. This one. We call it r perpendicular. Perpendicular to what? To p. Okay. So we call it the p-r perpendicular. If v parallel to r, then the angular momentum is 0. Example. Figure shows an overhead view of 2 particles moving at constant momentum along the horizontal path. Particle 1 with momentum magnitude P1, 5.0 kilogram meter per second, has position R1, and will pass 2.0 meter from point O. This is the distance. Particle 2 with momentum magnitude P2, 2.0 kilogram meter per second, has a position R2, and will pass 4.0 from point O. What is the net angular momentum? L about 0.0 of the two particle system. It's very simple. Just put in the formula. L1 equal to perpendicular RP1. Okay. Everything given. This is 2.0. This is 5.0. L2 equal to R perpendicular 2 plus P2. Okay. The only thing we have to notice is the direction. You see, RP, this is outward direction. RP, this is inward direction. So they are in opposite direction. So assume outward is positive, then this is negative. So when put them together, one is positive, one is negative. Newton's second law in angular form. We know Newton's second law in transform form. Sigma F equal to dP dt. P is the linear momentum. And when we do the angular relatively, then is sigma tau equal to dr dt for a single particle. Now let's prove it. Okay. What does this mean? This means the vector sum of all torque acting on a particle is equal to the time rate of change of the angular momentum of that particle. Of course, to the same orange. Let me prove it. You see, by definition, the angular momentum L equal to R cross mv. We do the derivative with respect to time t on both sides. This is two term. So what we do is we derivative the first term multiplied by 2. And when we derivative the second one multiplied by 1. And dr dt is v. So the v into c. And m is constant, take out. dv dt is 8. So this is m8. Okay? And we know v cross v is 0 because the angle is 0, sine 0 is 0. And this is a sigma f. Since r is one thing, it's only that one number. So we can put inside, you get a sigma r f. That is sigma tau. That we prove this one. dr dt equal to sigma tau. The sum of all torques acting on a particle is equal to the time rate of change of the angular momentum of that particle. Example. In a figure, a penguin of mass m falls from rest at point A down. Okay. This A is horizontally distance d from the orange O. And an XYZ coordinate system. This is X, this is Y. Z is outwards. X, Y, Z is outward. Okay. The positive direction of Z is directly outwards from the plane of the figure. Question A. What is the angular momentum L of the falling penguin about O? Now, by definition, it's very simple. R cross P. This is R at any time. P is going down, this one. R cross P by right-hand row is towards inside. It is a negative direction of Z, okay? Okay. So we put this, it should be R perpendicular P. R perpendicular what? R perpendicular to P. So this is one, this is a D. MV, V, because it's falling at rest, so V equal to GT. Okay, that's the momentum L. Question B, about the orange O, what is the torque on the pigeon due to the gravitational force Fg? The torque Fg around this one, by definition, is R cross P. R perpendicular F. R perpendicular is D. F is mg. Okay. From these two, we found dr dt is the DMG, right? The DMG is just equal to torque. This is the second law of Newton's second law in angular form.